Hi, so we're here with the August 2015 Regents exam Common Core. Start with the first 12 part ones here, and we'll go through those. So a parallelogram must be a rectangle when. All right. Now here's the trick on this. We've already said, or the problem already is telling us we have a parallelogram. So we already have opposite sides parallel. Both pairs, we already have opposite sides congruent, opposite angles congruent, all sorts of those properties because of the fact that we're starting out as a parallelogram. Basically what we're trying to say is, how do we upgrade it to guarantee it's now a rectangle? Well, you either need 4 right angles, actually even just 1 right angle would upgrade it. If we just had 1 right angle, the other 4 have to follow because it's a parallelogram. Well, that's not a choice. Okay, so now we go and we look at the choices here. Let's see, opposite sides parallel. We already have that, so that's not going to make it a rectangle. All right, we already have opposite sides congruent, so again, we can knock that one out. Now, diagonals perpendicular. You can still have diagonals perpendicular without having a rectangle. All right, it's called a rhombus. So if we upgrade from a parallelogram to this feature right here, all that guaranteed was a rhombus, which is all the sides are the same. So that's not going to do it. The diagonals congruent is going to be key here. In a rectangle, you have right angles in the corners. Let's see, opposite sides congruent. Now, if you draw on a diagonal this way, using Pythagorean theorem, you'll get that that's 13. Okay, you can go check that out if you'd like. Now, if we go with the diagonal the other way, it's going to be the same thing, because here you have your right triangle here. A squared plus b squared equals c squared. We're going to get both diagonals have to be congruent in a rectangle, and that's what we want. All right. Let's see. For an image to not be congruent to its pre-image, we have to use something that's not a rigid motion transformation. Now, this terminology just simply means keep the image and pre-image congruent. Okay, that's all this means. Okay, the list is, you've got line reflection, point reflection, rotation, and translation are the rigid motion transformations. The only ones that will change size are going to be stretch and dilation. All right, and that's going to be, stretch is not a choice. We don't work with that a whole lot, so we assume it's going to be dilation. Just check the scale factor. It is other than 1 or -1, so it is going to change the size. Okay, those other are all going to produce congruent images. All right, so this is tricky. This is a 3D spatial reasoning problem. All right, so we've got to get out of the two-dimensional mindset that we've been stuck in for a long time. We've got to go to 3D. We've got to imagine what's going to happen. That's what spatial reasoning is. You got to be able to imagine what's going to happen. We can't draw it. We're limited to 2D to draw, but we have to imagine a 3D shape. So we're going to take this, think of it like a flag, we're going to spin this around, trying to show you 3D here. Imagine that that's going around and around and around 360 degrees. What we hope that you can see, all right, is this rectangle will wrap around, okay, all the way around. So this is the rectangle part that got rotated, okay, and then that right here, that's W, or line W, from here to here, okay. And so what we have is a cylinder where that rectangle shape is spinning around here. You spun around that rectangle. Okay, so that's what it looks like. So cylinder is the term we're looking for. All right, this one, great problem. Usually what we have is, when we go to the basics of this, when we have a problem like, all right, what's sine of 50 equal to? And they'll say cos of x, right? And what you would do in this case is say, okay, these cofunctions are equal. Cofunction values are equal when the angles are complementary. When you're talking degree measurements, convert that to add to 90. All right, so if we have this problem, what we would pretty much do is 90 minus 50 to get 40. And sine 50 degrees is the same as cos of 40 degrees. And we could show you that on a right triangle, but really this is a memorized problem, right? Just make sure you understand this concept. I can go into more detail if you need it, but that's what we're looking for. We're looking for this relationship. Well, we don't see it. You know, it's not obvious when they talk about sine x. So what you have to realize is this one right here. If you add x and 90 minus x, basically you've got these two x's, the plus x and the minus x knock out, that is actually 90. So believe it or not, this is the answer we're looking for. A little tricky, but definitely one that you should expect, and a good problem to prepare for. All right, whenever we look at something that is going to carry the figure onto itself, the old term we used was symmetry. Basically, you're going to, what I like to say to my students is, we're going to cover the same outline. All right, and it's a little confusing with some of the stuff that we do. Carry on to itself, if you were to label this A and B, if we were to reflect, say, over the line, let's pick one, y equals 2. Let's go with CD, 2. So if I reflect over the line y is 2, this square is symmetric about that line. However, A doesn't land on A. A lands on D. So really it's like A prime right there. But D also goes to A prime. Or I'm sorry, D prime goes to A. So these points basically just switch, and every point on one side has a match on the other, so to speak. So basically every point maps onto another point that's already on the figure. So we cover the same outline. Think of it that way. So with y is 2, we did cover on the same outline, and we want the one that does not. Okay, y equals x is this line. Now with a square, the figure is symmetric about both diagonals. This line right here, that's the line. If you convert that, that's y equals negative x plus 4. And you can see that's 4 right there. And that's going with a down 1 over 1. So this is x plus y equals 4. This one's y equals x. So we're basically eliminating these. All right, x equals 5. If you reflect over that line, point A, let's get rid of that, ends up all the way over here somewhere. Well, we've just found a point that doesn't have a match on the other side of it. So we didn't fill the same outline. We're going to start, creating a new figure. So that is the one we're looking for. It does not carry on to itself there. All right. Okay, this one was interesting. What it looks like is that the dilation scale factor is 2. So they're saying which statement is always true. Now, we got to be careful. What it looks like, it looks like something happens is not enough. So yes, it looks like the scale factor is 2, but we can't be sure. It could be 2.1. It could be 1.9. So we have no idea for sure what happened. What we do know, when we dilate a line or a segment, such as, let's say we dilate any segment through point E, or sorry, centered at point A, we know that it's going to produce the same line or a parallel line right there. So DE is guaranteed to be parallel to BC, and that's all we're certain of. So that's what we have to circle. Now the other ones are tricky. AC does look like it's the same as CE, but nobody said K is 2. That's an assumption. Okay, if K was 2, then we would have those are true. Okay. All right. Taking a look at this. Now, what it looks like from this to this, there's a couple of possibilities. It could be a translation. It could be a rotation, 180 degrees potentially. But then you look at the positioning of the letters. Okay, if it was a 180-degree rotation about that point, A prime would be there. It's not a rotation. Translation's not a bad move, but if you translated, you'd have A prime here, and you'd have D prime there. So it's got to be a line reflection. It looks like it's a reflect over the line, the x-axis. So that's first move. It's one of these two. Now from here, okay, if we translated any amount, obviously we would keep this same sort of shape here. Okay, well, it got turned. There's no way a translation can produce this. So get rid of that. We've got a rotation. And that rotation is, looks like it is centered at this point here. Okay, and it appears to be, yeah, it looks like it's a 90-degree rotation centered at the origin. Not that we need to identify that, but it's good to go through that. All right. Okay, so what we're going to do is mark the diagram based on information such as that. Okay, it's a parallelogram, so a lot of properties there. And here we go. Angle R is 124 degrees. Opposite angles in a parallelogram are the same, so put 124 there. And we're really looking for that angle right there, AFD. AFD, right there. So I'm looking at basically a two-part problem. We started off right there, getting that from parallelogram properties, and now we have an exterior angles problem with isosceles triangles. Wow, we've got a lot. So we're looking for that basically. I would probably start out with 180 minus 124 to get 56. Base angles theorem of an isosceles triangle. Those angles opposite the congruent sides have to be the same. There's another way to do this problem, but this seems efficient for me. And we get 68 degrees there. Whoops. We want choice 3. All right, moving on. Okay, yeah. Looks like we want to get, yeah, equation of a circle in center radius form. So we're trying to get this format right here. That's our goal, okay? We've got a completing the square problem here. There's one way to do this. We could graph it, but that could get messy. I think that's our most efficient method. So what I tend to do with my students is tell them we've got to complete a square. We've got to end up looking like this. So there's going to be a number that we have to add in to complete the square of these three. And I'll show you what that looks like in a minute. Let's see. Okay, do that again here, because those three are going to combine. Keep the minus 12 equal to 0. And then whatever I add to the left, I have to add also to the right. Okay, so I'm going to go ahead a little bit. And the process, if you go back and look, I'll have to explain this more to anybody that has not been taught this way. So just email me and I can help you with that. But basically we cut it in half, and then we cut the middle term in half. Okay, that's what gets us this number. Then we think 2 squared is 4. Okay. Oops. Now we have this plus sign right here, and then these three are going to move into a perfect square. Again, cut in half. Y minus 3. Negative 3 squared is 9. So these two numbers are what complete the square. The 4 and the 9 are the two different squares that are there. We added it into the left, so we added it into the right. Okay, All right, and then 4 plus 9 is 13. We will add 12 to both sides. And now we have it in what's called center radius form. All right, let's see. Now we just want the radius. Well, this is the radius squared. So we square root both sides to get rid of that, and we get r is 5. All right, we're getting there. All right, so we've got to go parallel to this. The first thing I would do in this problem is calculate the slope. I like using rise over run. Of course, there's a formula you could use too. A lot of people use different formulas here. It doesn't matter if you go 2 minus 1. You'd use that. I like to go rise over run. And then I'll put the sign in on my own. The up and down is 6, the across is 9, and it's negative. Okay. Now, none of these have this. Let's see, they're all reduced, so I will reduce that. I can take out a 3. And so you get a slope of negative 2/3. We want parallel, so get rid of those. All right, next, you could do this algebraically, but since the graph's here, I'm going to use it. Down to right 3, or go up to left 3. There I ran into the y-intercept, y-axis to get the y-intercept, and it's up at 5. So there is my equation. All right, let's see, circular, okay. Diameter of 7, a square inside this. All right, so if I had my compass tool, I could show you this, but this technology won't let me do it. So I'm just going to estimate here. What we would do first is we would draw any random diameter. Okay, and then the perpendicular bisector is what we would need. So pretend like I actually did that construction. Because the diagonals of a square are going to bisect each other and be congruent and be perpendicular. Now, if we connect those, it is a square. Next, we want to know the length of the side. So let's pull this top. We'll pull this top triangle out. Okay. It's got a right angle. We were looking for that, and we know the diagonal or the diameter here is 7. Now, if you know your special right triangles, you would know that it's you could cut this in half times the square root of 2. So you could have 3.5 square root of 2 if you know that. If you don't know what I'm talking about there, that's fine. I can show you it's x squared plus x squared equals 7 squared. We'll just use Pythagorean theorem. Okay. And then square root both sides. And we get 4.9. Oh, this is what they're, wow, this is mean. 4.9475. Okay, so something we see a lot from students is they tend to round twice. They see this 49, round it up to 5, and then they'll round it a second time. You don't do that. This doesn't even exist if we're going to the nearest tenth. Okay, that's what you've got to tell yourself. The 4 is all that matters. The 4 is not big enough to kick this up, so we say it's 4.9. Okay, and that's what we got to be careful of there. All right, number 12. We've got some tangents, okay? So automatically a radius and a tangent are going to make a right angle. These vertical angles are congruent, so we have similar triangles, by the angle-angle triangle similarity postulate. Okay. So we'll have proportional sides. Gives us proportional corresponding sides. Safest bet is to go write the similarity statement. All right, I'll quick do that. So what I'm talking about is AOB, okay? And what it is it's going to be corresponding to PCB. So now your proportions are very easy to set up. If I want to use OA, the 4, right, it should correspond to PC, okay? And then if I want to use AB, it should correspond to CB. So now it's easy to just plug your numbers in. 4 is to 10 as 5 is to X, we'll call it. And yeah, that's what they wanted, so that's perfect. 4x equals 50. And what do we get there? I'll bet it's 12.5. Yes, it is. I just wanted to double check that. So 12.5 is the number we're looking for, and that completes the first half of the part ones. When this session, and pick up at the next batch.